Well, sheep babies are typically born in spring, which suggests this discrete time scale where the grid size is 1 year. And you could see that in our computations here, when n and k were only integers. So we didn't talk about size of our population about 1.3 years or something. We only spoke about 1, 2, 3, 4, 5, and so on. Okay. Other populations, think of tiny stuff like bacteria or viruses, reproduce in much smaller time intervals, which suggests to take models with continuous time. And typical models describe the size of your population by a differential equation, maybe like this. So here you say the growth rate or the reproduction rate is proportional to the current size of the population, right? So the more population you have, the more babies you're going to have in the next second. And we know that that leads to exponential growth. Or another model looks like this. The current reproduction or growth rate is proportional to both the current size of the population, but also to the number of individuals that is between the maximum number and the current number. And here, of course, we are all reminded of the current coronavirus pandemic, where you say, well, we have a certain number of individuals on this planet, and now F is not the number of little viruses running around or bacteria, it's the number of people that have been infected. And F max would be the number of people in the world, something like 7 or 8 billion or so. And then at first, when only a few people are infected, this factor is so huge that the whole behavior is governed by this part here. And this one remains roughly constant. So you start off with exponential growth, just like here. But then at some point, the number of individuals that are still healthy, so that you still can infect you as a virus, goes down, and thereby the whole spreading rate goes down a little bit, and it becomes smaller and smaller the smaller the number of healthy people is, because there's almost nowhere anyone to find that you can actually infect. And that is slowing down the whole dynamics, okay, until towards infinity you reach the limit. Well, now fortunately, with the current virus pandemic, people who survive the virus become immune and get back to healthy again and cannot be infected again. So that means the curve, in fact, goes down, and all the measures in terms of keeping distance from each other and so on are about getting this constant c that tells you about the speed of growth here to go down, right? So you want to, I mean, if you don't shake hands and if everyone stays home, then you're trying to get c to as small as possible, which has to do with this reproduction rate, and which is what people mean when they say you want to flatten the curve. Okay. Then sometimes you want to study more than just one quantity. So f here is scalar valued, f of t is just a number, but you could be interested in a vector because you're interested in, I don't know, rabbits and foxes and wolves and dogs and something else. And you have these 4 or 5 kinds of animals, populations that you want to follow, and you know that one eats the other, and you want to see the dynamics as time goes by. So that leads to the study of systems. And a typical model is just like this here. the derivative is in some sense proportional to the current size. But now f of t is a vector, and then f dash of t means every component of that vector as a function of t is differentiated by t, which gives you another vector with also same number of components. So it's a lot more appropriate and gives you a lot more room for models to not take a constant scalar value c here, but instead a matrix. Let's call it A. And of course, all the information about your foxes and rabbits and dogs and wolves is inside that matrix A. Who eats whom and why and how often. And then very similar to the solution of this differential equation here, we can explicitly write down the solution of that differential equation here also by an exponential function. But now this exponential function here is the exponential of a matrix. So you take the matrix A, multiply it by time, and then take the exponential of that. What that is, I'm going to recall in a minute. I'm sure you've seen that in Maths 3 course on ODEs, so systems of ordinary differential equations. And that f0 down here is just a vector like this, but at time t equals 0. So that just tells you how many rabbits and foxes and wolves and dogs did you have at the beginning of your little experiment. Okay, now let's recall what that exponential matrix exponential function is. So it goes by the same formula as the scalar valued exponential function in terms of a power series. And you have 1 over k factorial, and then times the argument of your exponential function to the power of k. And then of course we shouldn't forget about the vector f0. Okay, let's split this factor here quickly. And remember our sheep population experiment where we computed powers of a matrix A via diagonalization with eigenvalues and eigenvectors. And for simplicity, let's assume that A indeed can be diagonalized. So it can be written as a matrix X consisting of the eigenvectors of A in the columns, then matrix D consisting of the eigenvalues on the diagonal, and then this is X inverse. In general, you might have to take the Jordan normal form of factorization here, which is of course a bit more involved, but in the end leads to similar results. Okay, so if you plug that in for A here, then you get just like before X, then diagonal matrix to the power of K, and then X inverse. Okay, and now let's just assume our diagonal matrix is again, or our diagonal matrix entries, which are the eigenvalues, are again labeled lambda 1, lambda 2, and so on. Where here n is the length of our vector, right? So if you're interested in, what did we say, rabbits and foxes and wolves and dogs, then n equals 4. Okay, but now you can get this matrix X out in front of your summation and get all these sums and terms inside the matrix in front of each diagonal entry. And that gives you exponential functions, now scalar valued ones, for each of the diagonal entries. So you have e to the time times first eigenvalue here, and so on up to e to the time t times last eigenvalue down here. And now in general, lambda could be complex valued, so let's split that in real and imaginary part. Let's call them alpha and beta. And then write this exponential of a sum as a product of exponentials. And note that this here is just a point on the unit circle. So the whole question whether your population grows or is dying out depends on the real parts, little alpha of your eigenvalues, lambda 1 up to lambda n. So you get unbounded growth if alpha is positive. You go down to 0 if alpha is negative. And this term here remains constantly at 1 if alpha is 0. So for our population here, for the solution of our model, of our differential equation, we get that this grows unboundedly if, well, one of these diagonal entries here grows unboundedly, which means one of these eigenvalues has real part greater than 0. Or we could just say if the spectrum enters the right half plane. Okay, and similarly to the discussions before, your population will die out if the spectrum stays entirely in the left half plane and doesn't even touch the imaginary axis, so all of your eigenvalues have real part negative, strictly negative. Okay, and well, if some of them just reach real part equal to 0, so the spectrum would touch the imaginary axis but not cross it, coming from the left, well, then you would have roughly constant, or well, the size staying about the same behavior. Okay, so that's section 5.2 is here to remind you that the spectrum is important for many different things, and it's telling you what your dynamical system is doing when time goes to infinity. So for time discrete systems, think of our sheep breeding activities. You want the spectral radius to be bigger than 1 if you want to grow, or less than 1 if you want to go down to 0. So the spectrum should be contained entirely inside the unit circle or unit disk. Whereas for time continuous models like virus or bacteria spreading stuff, well, you want your model to die out, your population to die out, means spectrum should be entirely in the left half plane. Okay.